We're working some forward kinematic examples. We'll pick up with this example right here, and we're going to go through our multi-step process to work out the full kinematics. We'll start with this 6-off robot arm. It's got a revolute joint. Joint 1's a revolute. Oops. Lost him. Joint 1's a revolute. Sorry. I won't do it again. Joint 1's a revolute. What? Joint 1's a revolute. Joint 2. I can't. Every mouse is different. Joint 2 is a prismatic. Joint 3 is a prismatic, joint 4 is a revolute, joint 5 is a revolute, and joint 6 is a revolute. So it's a 6-off robot, N is 6. We've got theta 1, D2, D3, theta 4, theta 5, theta 6, the joint parameters. All right. So our step 1 is to label the joints. So we've got a joint theta 1 labeled here, a joint 2, D2 labeled there, a joint 3, D3 labeled, kind of, I'm trying to draw these dashed lines being the joint axis. Joint 4 here, joint 5 there, joint 6 out here. So that's step 1. Step 2 is to assign the joint axes, the Z's. And remember, we make Z0 lie along joint 1 and so on, okay? So I'll start here with Z0. Z1, somewhere along there. I don't really know where the origin of the frame is, so I just stick it somewhere along. Z2 along joint 3. Z3 somewhere along joint 4. Z4 somewhere along joint 5. Z5 somewhere along joint 6. Normally we come back and do the last joint later, or we could do it now. I've got it, I think, on a different step. Step 3, we assign the base frame freely, so I'm going to put it right down here. And the origin is where the X and the Z intersect. I'm going to put the X to the right. So that's step 3. That's my base frame. Keeps my base frame 0 down at the bottom of the robot. Let's see, step 4, we define the x's. Okay, so xi lies as the common normal between zi minus 1 and z. So that means x1 is the common normal between z0 and z1. z0 and z1 are collinear, so you can put it anywhere. So I'm going to keep it, I'm going to put it just like this. I might come back and change that at some point. I'm going to put it there for now. X2 is the common normal between Z1 and Z2. Z1 and Z2 intersect. Z1 is going up, Z2 goes to the right. So I'm going to use my right-hand rule. I don't know if you can see me, but I got my fingers pointing up in the direction of Z1, going towards Z2. That gives me X2 goes either into the board or out of the board. And you know what, based on, so that I'm good with the X2, I'm going to come back and change my X1. Since I was free to assign in any direction, I'm going to make my X1 and X2 line up. Okay, you don't have to do that. But I know later on the angle from X1 to X2 is a theta. And that's not a variable there. So I'm going to make those line up. Not a big deal. You could make them be 0. Or you could leave it where it was. Actually, I'm going to change it later. I'll show you explicitly later on when I want to change it. All right, next I have the common normal between Z2 and Z3. They're collinear, so I can stick them wherever I want. So I'm just going to have it be here at the center of this guy. I can put it wherever I want. So that would be my X3, and it's parallel with X2. X4 is a common normal between Z3 and Z4, so now I do have to use my right hand. I don't know if you can see my right hand by pointing my fingers in the direction of Z3. It's going to the right. Curl them to Z4 going up. That's my positive direction coming out. I am going to, once again, keep them all lined up. So I'm going to go back there. So it'll be the negative direction. I'm free to do that. X5 is the common normal between Z4 and Z5. Z4 is going up, so I point my fingers in the direction of Z4, which is up, curl them towards Z5. That again goes into the board, so the same direction, so that would be my X5. So that's step 4. Step 5 is the origin of each frame, and I've already done that. Step 6, compute the Ys. I'm not going to stick the stick. I'm not going to put those on. Step 7 is the end effector frame. So I assign my Z6 however I want. I'm going to just make it pointing out along my tool. That works. That keeps it collinear with Z5, which means I'm pretty free to put the origin wherever I want. And then X6 can be whatever direction I want. I could just make it line up with X5, but I am going to see that there's going to be rotations there. Right now they all line up, but they're all revolute joints, so they're going to start moving here in a few minutes. I say in a few minutes, as soon as I start rotating the robot. Okay, step 8, create the D&H table. So let's see, Bailey, you had a question on that. So let's now create our table. I have columns and I have rows. Okay, my columns are, I could start out with I for each joint. This is the joint, and each joint relates 2 links. I have a column for my A sub I, alpha sub I, D sub I, theta sub I, and then if I wanted, I could define the frame, the body, the links that I'm relating in my transformation. So my columns, my rows are for each joint, and I've got 6 joints. So there's going to be a row 1, row 2, row 3, row 4, 5. A little tight down there. Not the world's best table, but there we go. So I had 6 joints, so I need 6 rows. Now I like to go column at a time. So A's, so far so good?
Yes. Could you explain to me like the right hand rule?
Oh yeah. Okay, so we want to talk about the right hand rule. I don't know if you can see me in the camera. Drag the camera down here for just a moment. Hopefully you can see me down here. So Z0 and Z1 are collinear. Right-hand rule doesn't tell me too much. The right-hand rule says, I mean, it has to obey in all of them, but I got to cross Z0 and Z1. Well, Z0 goes up, Z1 goes up. So my thumb, you know, I've got to point in the direction of the one, curl them toward the second. So no curling, they're in the same direction. And then, you know, my X, my thumb is my X, and it can go anywhere. See, I can keep my fingers pointing in the direction of both Z0 and Z1, and I can slide it up and down. So that one's boring. Let's go to Z1 to Z2. So Z1's going up, and Z2 is going to the right of the paper. So I'm gonna rotate my hand around until I can curl to the right, okay? So Z1's up, Z2's to the right. That puts my thumb in the direction of the X. That's the right-hand rule. So it's Z0 cross Z1 gives me X1, okay? There's kind of 2 ways people do that. Sometimes they use the fingers. I do the curling my fingers. Sometimes they can, you know, and I guess there's different directions. So you could say like pointer finger is Z1, middle finger is Z2, and thumb is X. But I like curling. I like curling. So I point along the direction of Z1, curl towards Z2. Z2 and Z3 are collinear. So that one again, you know, I've got lots of options. Z3 and Z4. So Z3 is going is horizontally to the right. Z4 is up. So I got to curl my fingers towards Z4. So what I got to do? I got to turn all the way around until, oh look, now I can curl from Z3 to Z4. That puts my thumb coming out of the board. In this case, I chose to go in my negative thumb direction, which would be the left-hand rule, but we never do the left-hand rule. So I'm choosing the negative direction. That'll show up in my table because I didn't say, it could either be the plus or minus direction. Okay, Z4 is going up, curl my fingers towards Z5. Z5 is to the right, so this is natural. So if I'd gone up like this, I'd have to turn my finger. Z5 is going that way, so I got to turn my hand all the way around Now I'm curling towards Z5, so my thumb's coming out of the board, or into the board, excuse me. So that's my X5. And then Z5 and Z6 are parallel. Yeah, yeah. Okay. So now I've got to do my A's. My A is the distance from Z0 to Z1 measured along, or yeah, Z0 to Z1 measured along X. It's along the current X, so along X1. So Z0 and Z1 are intersect. Z1 and Z2 intersect, right? Z2 and Z3 intersect. Z3 and Z4 intersect. So the distance, if they intersect, the distance is 0. Z4 and Z5 intersect. Z5 and Z6 intersect. That column was easy. Well, if for some reason there was an offset and Z0 is over here. They don't intersect. So now I'd measure the distance along X1. So it'd be this distance. Yep. Yeah, it's weird when they don't show up. But if in this case they all happen to intersect. But yeah, I could have an offset anywhere. I could take this robot and put an offset in any of these links, and that would do it, right? So if I took this link up here and shifted it, that'd make an offset. All right, alpha. Alpha is the angle between the Z's. So it's the angle between Z0 and Z1 measured along it, about X1. So Z0 to Z1, they're collinear. They go in the same direction, okay? Z1 to Z2, about X2, okay? So remember, Z1 cross Z2 is about X2. So I basically had to curl my fingers from Z1 to Z2, about X2. I had to curl them positive 90 degrees. I measured the amount of curl I have. So that was a positive 90. Z2 and Z3 are parallel. They're collinear. Z3 and Z4. So as Z3 was going horizontal, Z4 was going up. So X4, I said should come out of the board, but I chose into the board. So I'm going to take my thumb and point along the X4. My fingers are pointing in the direction of Z3. Around this thumb, X4, how far do I have to rotate? I either have to go negative, negative 90 for my right hand, or I have to go positive, 90, 180, 270. So either one is fine. Negative 90 or 270, they're both the same answer. Z4 to Z5, take my thumb, point in the direction of X5, point my fingers in the direction of Z4, which is up, curl them until they point at Z5. So this one's a positive 90. And Z5 and Z6 are parallel. Now I go to my D's. Distance from X0 to X1 measured along Z0. Well, that's this guy. So that's D1. Not really labeled there, but there you go. Distance from Z1 to Z2, or excuse me, from X1 to X2, measured along Z1. Well, that's this guy. D2. Distance from X2 to X3, measured along Z2. This guy, D3. Distance from Z3 to Z4, measured along Z3, that's D4. Distance from X4 to X5, they are intersecting. 0. X5 to X6, measured along Z5, it's going to be D6.
So why is the X5 not the Z? Like, I mean, I guess, why is the placement like that for X5?
Bailey's asking, why is say it again?
Like, why is the placement the same as like the Z4? Or sorry, X4.
Why is X4 and X5? Why are they intersecting?
Yeah.
Because he didn't have a choice. Okay, so Z3 intersects Z4, so X has to pass through this point.
Okay.
Z4 and Z5 intersect.
Okay.
Also at that point. So X5 has to pass through that point. So the distance, really you're measuring the distance from this point to this point, right? X5 intersects Z5 here. X6 intersects Z5, Z5 here. So you got to measure that distance. That's D6. But yeah.
Oh, sorry.
Yeah.
On your notes, you put asterisks beside.
Yes. Okay. So then the question about asterisk. So the asterisk represents the joint variable. So it wouldn't hurt if we did that while we were doing it, or now. D1 was constant because joint 1 was a rotation. D2, joint 2 was changing length, right? It was a prismatic. So I want to indicate that on my table. It'll help me know what's going on. Joint 3 was a prismatic. That means the length along Z2, which is the direction of joint 3, I know that's confusing, changes. Here I could put it next to these guys too, so you can see those lengths change. The rest of these are constant. That distance is constant. D4 is constant. D6 is constant. Now let's go to my thetas. So maybe we'll do it. We'll put the asterisks as we go. So theta 1, that's the angle between x0 and x1. Looks like they're lined up. Looks like it'd be 0, but theta 1 is joint 1 is a revolute. So that could change. It's shown as 0, but it could change. So I got to list it. Wouldn't put 0. I wouldn't put 0 with an asterisk because how does 0 change? It's 0. You got to put in the variable. All right. What about theta 1? Now look, theta 1, or excuse me, joint 2. The angle between x1 and x2 measured along z1. Well, that's the rotation around joint 2. So it's that guy. Joint 2 is a prismatic. It does not change angle, so that's a constant angle. So here it's shown as 90. Okay, here it'd be 90. See that? Now, if I wanted to make as many zeros as possible in my table, I might say, you know what? I prefer that to be 0. How could I make it 0? Well, it was kind of, was free to choose x1. I could just drive x1 to be back here, make it line up with x2. That would make that guy go to 0. Remember, I did that early on, but then I said, no, let me not do it. Now is a chance I can think about it. You are free to do it either way. You're free to do it either way. You can, you can leave it going to the right, like you did at first, and then put a 90. I mean, you can go crazy. You can stick it out this way and say, that's, 137.5 degrees. You don't want to do that. You want to simplify this table as much as possible. You saw that in the multiplications. 90 is not bad. I really like zeros. 90s aren't bad. I'm going to choose to go ahead and make it 0 now. Okay. x2 to x3. Right? Now it shows 0 on the table. Right? But we got to ask ourselves, is joint 3 a revolute joint or is it prismatic? If it's a revolute joint, then even though they line up, I got to call theta with an asterisk. If it's prismatic and they line up, they're never going to change. Looks to me like joint 2 is a prismatic. It's that D. So I've already, in this case, I by default chosen to line up, so I'll leave it at 0. I could have chosen some other direction, right? I could have had a non-zero value. It's funny how sometimes you have choices and sometimes you don't. That's why I'm trying to talk out loud, where we do and where we don't. Okay, now, angle between x3 and x4 measured around z3. Well, it looks like they're lined up. It looks like I'd put in a 0, right? But I got to check. What's that joint? Joint 4. Well, it's a rotation. So I got to put in a theta. Even though they're lined up, the minute I start moving, that thing's going to change. So it's a theta 4 is a joint 4 is a revolute joint. So we're going to put in theta 4. I'll put the star indicating it changes. Whew. X4 to X5, measure on Z4. They're lined up. I would think 0, but I got to check. Look, joint 5 is a revolute. So I got to put in theta 5. X5 to X6, looks like they're lined up. But again, it's a revolute joint. So we're going to put in theta 6. So that's the table. If you want, you can go ahead and list that the first column is, projection of 1 to 0, 2 to 1, 3 to 2, 4 to 3, 5 to 4, 6 to 5. Okay, so that was step 7. Step 8, that was step 8 actually. Step 9 is a transformation. Step 9, I got to create all these guys. So I now look at the table and create all of them. Let's create a couple at least. So, I've got that. I've got that, remember I've got this, this guy. I don't know can't pull those up on there. All these years I've been using OneNote, and I still can't figure it out. Anyhow, there it is. It's down there. We can peek at it a little bit at least. So row 1 is cosine theta 1 times, second row is negative sine theta 1 times the cosine of alpha 1. Alpha 1 is 0, so cosine of 0 is 1. So I get negative sine theta 1. Third column is sine theta 1 times the sine of alpha 1. Alpha 1 is 0, sine of 0 is 0. Last row is A1, which is 0 times cosine theta 1. Second row, I get sine theta 1, cosine theta 1 times cosine of 0, which is 1. Negative cosine theta 1 times sine of 0, that's 0. And then A1 is, once again, 0 times sine theta 1. Third row is 0, sine of 0, sine of alpha is 0, cosine of alpha is 1. And then I get D1, which exists, so I can put a D1, and then 0, 0, 0, 1. Okay, that's my T1, 0. T2, 1. Looking at my table, so far so good? This part was okay?
Yeah.
So the first row is cosine theta 2, well, to 0. So that's a 1. This one's weird. You know, you don't get too many thetas equal 0, right? I mean, don't complain. It makes your robot easier. Second row is negative sine theta 1, sine of 0 times the cosine of 90. Well, that's 0 times 0. Next one is sine theta 1, sine of 0, which is 0. And the last one is A1, which is 0 times the cosine of 0, which is 1. Okay. Whew. It's a lot of 0 and 1s, I'm saying. Second row is sine theta 1, which is 0. Cosine theta 1 times cosine of alpha, that's cosine of 90, so it's 0. Third one is negative cosine of 0, so that's negative 1 times the sine of 90, so that's going to be negative 1. Fourth row is A1, which is 0 times sine of 0. Third row, 0. Sine of alpha, alpha is 1, 0. And then D. I keep saying 1s. I should have been saying 2s. We're on row 2. Do a find replace on the last things I said. Replace the 1s with 2s. I don't know how long I've been making that mistake. I don't want to go back and fix it. I think we're okay on that. And they keep going. Going to do the same for T3, 2. You know, okay, T3, 2, now I've got theta 3 is 0 and sine of 3 is 0. So I get 1, 0, 0. I'm just going to do, and then 0. Second row is sine of 0, cosine of 0, cosine of 0, negative cosine 0 times sine of, wait, I did that wrong. Cosine of 0 is 1 times cosine of alpha, which is 0, is 0. So that's a 1. 0. Then 0, cosine, sine of 0 is 0, cosine. So that's the identity. The third one is the identity, which I guess makes sense. It's just a bunch of zeros. And then a D3. And you just keep going. These were kind of pretty, not pretty. These were a little shorter because I don't have the thetas. I didn't have a theta 2 and theta 3. Now I'm going to start putting them together. I mean, I'd finished my transformations. I'm only halfway. So T21 is T10 times T2 on 0 is T10 times T21, which would be, you know, or you could write it like this. You could say T30 is T10 times T21 times T32. I'm going to multiply those two first. That's going to give me T2 project on 0. So let's do that multiplication. Not allowed myself much room. First row times first column. Cosine theta 1 times 1 plus 0 plus 0. So it's cosine theta 1. Second row. Cosine theta 1 times 0 minus sine theta 1 times 0 plus 0 times 0, 0. Third row is cosine times 0, sine times 0, 0 times D1, D2. We have a mistake. Oh no, Bailey, what did we do wrong? Oh, we just did our multiplication wrong. Okay. First row times the third column. Cosine theta 1 times 0, negative sine theta 1 times 1, negative 1, so that's positive sine theta 1. Last column. I skipped to the last column. So cosine theta 1 times 0, negative sine theta times 0, 0 times d2, 0 times 1. So that's all zeros. Whew, second row. Sine theta 1 times 1. Second column is 0. Third column is negative 1 times cosine theta 1. Fourth column is 0. Third column is 0, 1, 0, d1 plus d2. Fourth row is 0, 0, 0, 1. Okay, I did that multiplication in my head kind of quickly. Now we got to multiply by t3 on 2. So if we multiplied all this guy times that last column, we're going to get first row, cosine theta 1 times 1 plus 0, 0 plus 0. Second row is cosine times 0 plus 0 times 1 plus sine theta is 1, so that's 0. Third column is sine theta 1. Fourth column is sine theta 1 times d3. Second row is sine theta 1, 0, negative cosine theta 1, negative cosine theta 1 times d3. Third row is 0, 1, 0, and then d1 plus d2 plus d3, 0, 0, 0, 1. That is t3, 0. And I just keep going. Now, because theta 2 and theta 3 were zeros, this really came out quite simple, right? I only had the theta 1. If you've done a few of these that are a little more involved, it is, I would need a full piece of paper to write the one matrix down, right? And then it just gets worse from there. I mean, it really becomes a mathematical, just a lot of terms. Repetitive, lots of terms. Okay. I keep going. You know, then I would multiply this times t4 on 3, multiply by team 5 on 4. And then when I'm all done, the very last step is I would say that, look, once I got t6, 0, I'd say that the position was contained in this, the last column, first 3 rows. That's the position of the end effector. And then I would say that the orientation is the first 3 columns. That's the orientation. And to remind myself, well, what direction is the z-axis pointing? That's the third column. What direction is the x-axis pointing? It's the first column. That's the unit vector that defines that axis. All right, more multiplications. Okay, so let me going to stop recording.